So I'll talk about thermoacoustic emissions generated during particle therapy. I'll talk a little bit about the analysis that I've been working on and just briefly mention some truly tomographic applications. Now, particle therapy is used to treat solid tumors rather than X-rays because, as many of you know, X-rays obey Beer's law and deposit dose according to an exponentially decaying curve, whereas charged particles that enter the patient at relativistic speeds, they obey the Bethe-Bloch equation, and they really concentrate dose as they slow down. So as they enter the patient, there's very little time for electromagnetic interactions to slow down that particle and exert a force. But as they slow down more and more and more, there's more time. And so more dose is deposited as they come to a stop. And so the great news is, since they actually stop, you have the opportunity to protect radiosensitive organ at risk, or an OAR. So in this picture, I've shown for you a dose map in color and a tumor represented by a gray star. And if the tumor is next to a very radiosensitive organ, or if it's in the brain, where everything is an organ at risk, in principle, particle beams are great because you can treat the tumor and spare the radiosensitive tissue. Well, that's in principle. In practice, if the patient moves, you could fail to treat the tumor altogether and do no good whatsoever. Or if they move the other way, you can clobber that radiosensitive tissue while you're undertreating the tumor. So it's very important to line up the patients every day. And when you visit a clinic, you can see that they knock themselves out to take an X-ray radiograph and align the bony structures that they can see very well with the planning CT volume that was acquired a week or two before. So the bony structures are lined up very well, but the soft tissue, it can change on a daily basis. And indeed, the point of radiation therapy is to damage the tumor. So if that tumor shrinks and some serous fluid develops around it, you can actually have a change in the range of the beam simply because the material that the beam interrogates has changed. So a soft tissue range verification technique that functions in real time or close to real time is critical to really make this technology applicable to many tumor sites. Currently, it's primarily used in the brain and for central nervous system type of applications. Okay, so now let's just talk a little bit about the physics of what's going on. And I'll just talk qualitatively here, because the effects are mind-blowing. When you think about a single proton, with a very tiny diameter, entering a patient at half or 2/3 the speed of light, it generates a shock. When you deposit 10 million of them in a few microseconds, what actually you get at the end is a low frequency acoustic signal, very low frequency. And these signals, they propagate, they're refracted a bit, diffracted, reflected, and they're absorbed. And so we'll talk about the different absorption phenomena, which is you have strong absorption from the single, the track or the acoustic pulse created by a single particle, but very little absorption of that aggregate signal. And then, of course, if you want to do anything with it, we have to think about, what do we actually measure? And so I'll talk about how our receive chain, and the one that I've developed, really band passes the signal. And then I'll talk about the work I do. I'll give a little interlude talking about the work of others that really do tomography with this data. And then I'll talk about, at the very end, if I have time, incorporating a priori information to beat the diffraction limit and really localize that Bragg peak, that treatment spot, with sub-millimeter accuracy. Okay. So, and I should also mention, if there are any questions along the way, please just shout them out and let me stop. The units that we're talking about, typically when we do thermoacoustics, we're interested in pressures or pascals. So it's an energy density. And just to give you a sense of the scaling in some of the slides I'll show you next, 1 keV per cubic nanometer is equal to about 10 to the 10 pascals in water, or 10 to the 5 atmospheres of pressure. So incredibly high pressures. And so when we think about shock formation, here's a classic example that's taught in freshman physics. We have a bullet traveling through air. And you can see the Mach angle is just a little bit above 1, and we've got a cone angle of about 60 degrees. Okay. But when we talk about a proton entering at about 10 to the 8 meters per second and in fluid or in soft tissue with a propagation speed of about 10 to the 3 meters per second, well, then you have a Mach entry of about 10 to the 5 upon entry. So your cone angle is nil. And so you basically have cylindrical propagating wave fronts for these shocks. And this was analyzed very carefully in the early 90s by Bob Apfel and his colleagues Sun and Nath. So I'll just show you some of the plots. And we have some numerical people in the crowd. You can imagine trying to track these wave fronts. They're so incredibly sharp or broadband is non-trivial. It's a very difficult numerical problem to solve. So I think we should look at these plots qualitatively, but still you can see you've got hundreds of degrees temperature rise within just a few picoseconds or less than a picosecond at a cylinder of varying radii here. So I hope you can see my mouse, but they analyzed for these cylinders about the proton track for a particle at relatively low stopping power. So this keV per micron represents the stopping power of the material on the proton. So before it's really started to slow down, you see these sorts of temperature rises in very, very small volumes. And they give you extraordinarily high internal energy densities in these small volumes. And again, this temperature gradients are astronomical. They're just huge. Now, at 40 keV per micron, the particle is really starting to slow down. So now we're talking about the region where the particle is stopping. A year later, in '93, Sun and Nath actually did very similar computations in a medical physics paper, and they included the pressure computations, which of course is what I'm most interested in. So now you can see that at a radius of 0.4 nanometers, you've got pressures on the order of 80,000 atmospheres, incredibly high, but they don't endure very long. And more recently, I should mention, Eugene Sidortovich outside of Detroit has been doing some analysis as well. Now, you've got an incredibly sharp wavefront. So a very broadband pressure pulse is being generated. So it's a little surprising to me to see that there's no rarefaction in these plots. At least we can't see it. But one thing we should also note is that it's absolutely no surprise that the decay is so quick, because when you think about it, you're talking about frequencies on the order of 10 to the 12 hertz or 1,000,000 megahertz. And any attenuation model that I've seen is a function of frequency and increases, the attenuation coefficient increases with frequency. Now, the attenuation models that have been developed for water at room temperature probably don't hold at these very, very high temperatures and extremely high pressures, but it all holds together that this model supports very fast decay of our pulses generated by a single track. But of course, during proton therapy, you don't just have one track, you have many. And so you can imagine, and I'm just showing you here a few ion tracks traced by TRIM, Monte Carlo software. If you've got 3 tracks, 4 tracks, 5 tracks, 9 tracks, you can see here that these particles, they don't enter at exactly the same place because they are charged particles. They repel each other a bit. It's hard to control them. They don't all have exactly the same starting energy. So there's a bit of a standard deviation in the energy. So you expect a bit of a difference in the depth that they travel. And additionally, they scatter as they slow down. So they spread out a bit. Okay, so the simulations I've done, I'll show you shortly, was to model a clinical synchrocyclotron that we've done work with. So now here, let's just think a little bit about what happens when we've got many, many particles entering. So assuming that we can deliver all of the particles instantaneously, you would get a positive measurement at receiver located outside of the beam, followed by a weak rarefaction pulse. And let's see if I can run this movie here. Yeah. So you can see the positive pressure and then the rarefaction that will follow. And I'll let it go for a little bit more. Okay. But now I want to wind it back and make a point that we've been relying on experimentally so far. It's that if you place a transducer distal to the Bragg peak, distal to the treatment spot, you get a much sharper and stronger pulse than you would get if you placed it laterally. So in the experimental setups, we really try to put our receivers downstream, distal to the beam. And so if we do that, for the very first experiment I did at Lawrence Berkeley lab, 4 picocoulombs of charge were delivered in a pulse. Now, if they'd had the ability to do a single turn extraction and deliver essentially instantaneously, this is the signal I would expect to have received with about 60 pascals, because they really delivered a lot of dose with a low energy beam. But that wasn't possible. So what the guys were able to do was deliver 4 picocoulombs over 2 microseconds. And the cyclotron delivers particles in bunches at 10 megahertz repetition frequency at LBL. So instead of getting that one big strong pulse, the first bunch of particles that came in generated that red pulse that you see, this small one. Then the second bunch came in. So now you see 2 blue pulses here, and they're pretty coherent. So we got pretty good amplification. Then the third pulse, then the fourth. And, in the 2 microsecond pulse duration, 10 megahertz, we got about 20 pulses. And you can see that we still got some signal, and we were able to detect it, but it's much weaker. We lost a factor of about 6 in amplitude, and it also has a much broader bandwidth. So we lost frequency content, lower bandwidth, I should say. So this really is Duhamel's principle in action. And it says that you need to obey stress confinement and build up the pressure faster than it can run away. And in soft tissue and water, that propagation speed is about 1.5 millimeters per microsecond. So if you extend your pulse duration to 6 microseconds, I did this simulation because that's the pulse duration delivered by some clinical systems, then you see that for this low energy beam with a sharp Bragg peak, we get a real loss, even greater loss in amplitude. And we almost achieve steady state before we see the rarefaction pulse at the end. So you lose lots of information when you can't obey stress confinement. Okay. Now, let's just quickly go through some analysis here. For this isochronous cyclotron, it delivered 49 MeV protons at the 88-inch. And the pulse duration, so this is the temporal pulse envelope that I'm showing you now in the lower left, had a full width half max of about 1.76 microseconds. And when we do the spectral analysis and look at the frequencies of the pressure that we expect to measure, so I just take the FT of the pulse I showed you on the previous slide, that's in this thin line here. You can see the frequency content peaks at about, 450 kilohertz, but extends out to a couple of megahertz. But the Fourier transform of this signal, of my pulse envelope, it dies very quickly. And it really bombs out at about 700 kilohertz. So the signal that was actually excited is the product of these two things due to the convolution theorem. And so we can see that my signal was much lower than the sensitivity band of the receivers that I was trying to use. So we used a Verisonic system in this very first experiment and had to average 1,000 times in order to pick up a decent signal to noise ratio. In the next experiment, I used a LINAC at Argonne National Lab in Chicago. And that delivers lower energy protons with an even sharper energy deposition profile. So you expect that it would generate an even higher frequency acoustic signal if you can obey stress confinement. Well, that requires delivering very short pulses, which they can do at Argonne. So they can deliver about a 10 nanosecond individual bunch, and they can deliver one bunch at a time. Because I was working with an ultrasound system, I said, let's deliver 2, 3, 4 bunches. We'll still be stress confined and within the frequency spectrum of my receivers. And so when we did that, now you can see we are talking about the frequency being band limited to 4 or 6 megahertz, which was just about right for the P41 array that I was using with my ultrasound system. And we could also, because we tuned now to the receive sensitivity of our acoustics system, we could detect a single pulse rather than having to average over 1,000. Okay, finally, clinical synchrocyclotrons, they deliver much, much higher energy protons that travel much, much deeper in the patient. They spread out more. The Bragg curve is much smoother. And they deliver over about 5 microseconds. Now, if you notice the spatial scales here, now we're talking centimeters rather than millimeters. And so the requirement, the travel time across the Bragg curve is microseconds. So a 5 microsecond pulse duration isn't really such a bad thing. And when we look at the spectral content of a pulse delivered instantaneously in thick black, as opposed to delivered over a 5 microsecond or a 10 microsecond pulse duration, we lose a little bit, but nowhere near as much as we lost in Berkeley. So we're pretty close to stress confined, and I'll take it. As an experimentalist, I'll take that. So, and one other point I want to make though, is now, because my frequencies are so low, we're down around 50 kilohertz, say, lambda over 2 diffraction limit is 15 millimeters, which of course is not acceptable. We need to be much, much more accurate. So we need to think about this not in terms of an imaging problem, if I want to localize where the treatment spot is, but rather think about it a little bit differently. Okay, so now as a practical matter, this is more of an experimental aspect. My acoustic receive chain, it band passes the signal. And also, I just want to point out experimentally for these clinical systems, which I've really been working with the last couple years, they deliver on the order of 10 million protons per pulse. Well, that's about 1 picocoulomb. And the rule of thumb, if it stops in soft tissue or water, is that it's then generating on the order of 1 to 10 pascals per pulse. Now, therefore, we have to amplify. A pascal is not much. We live at atmospheric pressure, most of us, at about 10 to the 5 pascals. And clinical transducers they transmit and then receive, and transmitting on the order of an atmosphere is not at all unusual. And then they hope to receive, thousands of pascals of pressure. So we really have to amplify a lot. So I just want to show you how we've characterized in my lab, sending a signal through the amplifier. We have to attenuate before we amplify, because we're amplifying so much that if I send in a signal that I can actually measure on my oscilloscope to my amplifier, I blow out the amplifier. So I had to attenuate, which is my SB signal. And you can see the attenuator is pretty faithful. It doesn't do half bad job, that 40 dB of attenuation. And then my amplification is good. So it gives me more than 40 dB of amplification, but you can see the pulse shape has changed. And so in the spectral domain, if I take the FT of each one of these pulses, I see that, well, it looks like the amplification is a little bit lower at the higher frequencies. And really what we do to get this amplification number in terms of dB is to divide the amplified signal by the input signal. So we can see that we're getting between 48 and 44 dB of amplification. And I'm actually quite pleased with this plot because previous amplifiers bombed out between 50 and 100 kilohertz. So we have a broader band and flatter response than we've seen in the past. And then when we include the impact of our transducer, what we actually get is this scaling here, and I should have added a label. It's dB relative to 1 Pascal per millivolt. Okay. Now here, let me just mention the folks who've really been doing true tomography with these thermoacoustic emissions are Keith Stantz, Vadim Moskin, and Alcinia. And in 2015, they published a paper in Med Physics, which I recommend to those of you who are interested in applications, where they said, look, the photoacoustics community has shown us, and the mathematical community, that there are mathematically exact reconstructions available. We can apply and measure on a cylindrical measurement aperture, collect mathematically complete data, and reconstruct quite accurately, in principle, the dose map. So they're proposing to use thermoacoustics for dosimetry and actually quality assurance on the machines to verify in a water tank that the dose that you think you're delivering is actually what you're delivering. What I'm doing is a little bit simpler than that, much simpler. I'm trying to range find based upon a very limited angle data set and undersampled data set. So here, let me just show you my measurement aperture is just these 4 receivers, 1, 2, 3, and 4, packed around a wireless ultrasound array. And just to give you a sense of the dimensions, this is 3 centimeters across the length of the array. So the receivers are about 5 centimeters apart this way and maybe 2 centimeters this way. We've got an optical scan so we can get very accurate locations of these receivers relative to the ultrasound imaging system. Because my game plan is collect an ultrasound image and then use that to locate and determine exactly where my receivers are located relative to the object. So I'll show you that in just a moment. The setup we had in Newcastle, UK, so in the last few years, the United Kingdom has installed many proton therapy systems, and the Rutherford Cancer Centers have installed several of IBA's synchrocyclotrons. And to be candid, they've had not quite as much business as they thought, so they were able to give me beam time, which was great. So I gratefully took advantage and flew over there before the pandemic, and we collected this data. So I chose a multimodality imaging phantom that's mostly made of gelatin, except for some bony inserts that represents ribs and the spine. And this phantom is designed for CT, MR, and ultrasound combined. The folks at the Rutherford developed a treatment plan shown here. And my thought was initially, okay, I'll put my receivers right there and listen as the beam is being delivered. Now, this is an aggregate treatment plan representing the total dose delivered by many, many different beams. But as we thought about it for our very first experiment, I was nervous about having my beams my transducers so close to the proton beam. So I asked them to insert a range shifter and just pull the dose back so that my acoustic hardware wouldn't get any neutron radiation, or get minimal, I should say. So that was our setup. Here are some photos, and we placed this hydrogel phantom. One of the techs there was very clever, and he recommended using a vac bag to secure it. So the ultrasound system is resting on that vac bag, and we've got amplifiers and 4 receivers tucked underneath. It's hard to see them. And all of this was secured together by a custom clamp. we used the same gamma detector that we used in Berkeley, which was developed by the late Alan Jackson. And I'm very grateful to be able to use that detector even now. And then we used a digital scope for remote readout. Now, we needed to pinpoint the receiver locations, and I don't want to belabor this, but we simply used the information about the relative position of the receivers to the ultrasound array and combined that with co-registration of the ultrasound image here to a reformatted CT image, a tipped plane in the CT. And here you can see, because the contrast mechanisms between ultrasound and CT are so different, but you can see these inclusions in the CT match up very weakly with the ultrasound. Okay, so we know where our receivers are located. Then we did some Monte Carlo simulations as well to predict what kinds of signals we would get. And I have to say that Mariko Hillis and Kevin Souris in Belgium were tremendously helpful in utilizing this Monte Carlo package. The K-Wave acoustic software, which I'm sure many of you are familiar with, was then used. So we took the dose maps created by the MC2 package, and those modeled the dose as it was truly delivered into the Phantom. So we took the system log files and used those to create the dose maps or energy density maps, fed that into K-Wave, and used the material properties of the gelatins in that Phantom, which were quite well known. We had to do some additional measurements to get some of the thermal properties. But CIRS, the company that makes the Phantom, knows a lot about sound speed and density of the materials in their Phantoms. That's their job. We were able to compute the Gruneisen pretty accurately, I believe. And also, since we had the gamma detector measurements of the pulse envelope, we were able to account for that pulse envelope in these K-wave simulations. Okay, so let me show you the results. The simulated signals are in thin lines and the measured signals are in thick. Okay, and so we've got 4 measured signals from the 4 acoustic receivers. The red and the blue receiver locations are up above, more or less distal to the beams. And then the magenta and cyan are a little bit lateral to most of the beams. So here you can see an individual beamlet that comes in. And the black pulse, I should also mention, represents the gamma detector. So this is like an approximate delta function. Now, for this particular beamlet, the path from the Bragg peak, the bright spot, to the uppermost blue and red transducers was clear. It passed right through all soft tissue. To the cyan and magenta transducers, it had to go through bone, so it was largely reflected. And you can see that. We got very little of the magenta and cyan signal, but the blue and the red, we got something. And you can see the amplitudes are only on the order of a millivolt, really very weak, but we got something. And here's a spot map showing a treatment layer. So we're treating now spot number A here. And you can see that the simulated signal is 0 until the arrival, whereas the measured signals have some junk. And there's a real question as to whether that junk is electromagnetic interference or simply the fact that the proton therapy system pulses at a kilohertz repetition rate. And at these very low frequencies of our aggregate signals, there's very little attenuation. And so there may be some actual wraparound effect. Okay. Now, if we look at pulse from beamlet, I believe number M over here, this beam partially stopped in bone, and the bone has a much higher Gruneisen. So the signal was really much stronger, markedly stronger. Also, you can see, even in the transducers for which the signal just traveled straight up, there were some multiple reflections in the bone that you can see in the simulated signals. Now, my received chain is so low frequency, it just didn't pick up those high frequency oscillations at all, but agrees. And if I band pass the simulated signals, I get the dashed black lines, which agree pretty well with the measurements. What was interesting and quite surprising that I could see during the experiment was that my other two channels started to pick up signal, but not in ways that I expected. It's just ringing. The cyan channel is ringing. And I think that's because the frequency content that was actually created was above the bandwidth of my receive chain. And so it just started oscillating at its resonant frequency. So the upshot is, when your beam stops in bone, you may get some surprising results, but it's often clear that you've stopped in bone. Okay, so simply using the upper two transducers, for which we got pretty good signal from most beams, we were able to estimate the range using the treatment spots that received the most dose. And let me go back for just a moment. These are treatment spots in the second layer that was treated in the patient. Now, 12 layers were treated in all. The layers go from top to bottom, layer 1, layer 2, layer 12. So the first few layers received the most dose, and the size of these circles represents the amount of dose delivered to the spots. Now, because we want to, because we get the cleanest signal when the transducers are distal to the Bragg peak, we tended to use treatment spots more on this side, and the treatment spots in here tended to stop in bone. So I'll focus my analysis on these treatment spots. I believe it was A through F. And when we do that, we see that these beams that stopped in soft tissue, the initial pressures were quite weak, on the order of 5 pascals. Now, what I want to do is just tell you how we process the data. By incorporating a priori information, we know a lot about the target, we know a lot about the patient. So we simulated not only the beamlet for the treatment plan as prescribed, but for also higher and lower particle energies entering. So we ran 9 simulations for delta energy levels from -4 to +4 MeV, and those simulated pulses are shown in black. The measured is shown in blue. And for each one of those simulated pulses, we know precisely the Bragg peak location. We know that to the accuracy of the planning CT, which was 1.19 millimeters. And so by interpolating in time, we say, okay, this part of the pulse is rising approximately as the second and third. So we interpolate in between those, just linearly interpolate as appropriate, and also interpolate the Bragg peak locations to estimate, and we do that for both channels. And now my computer's a bit stuck. Oh, there we go. So we did that for both the blue and the red channels, averaged those shifts that we estimated. And when we look here, we've got pretty good accuracy. So average was 200 microns off of what was predicted for the phantom, with a standard deviation of about 700 microns. Well, 700 microns is much less than the pixel pitch in that planning CT. So I'm quite pleased with that result. Okay, and these results will appear in the Green Journal, hopefully this spring soon. It's been accepted. And what we did in terms of analysis here is a simplified version of the two-step method. So I'll refer you to an old med physics paper for that if you're interested. Now, one point I want to make is that clinical medical physicists, they really care about knowing the Bragg peak location in absolute coordinates, right? They want to know exactly where that Bragg peak is so that they can position the patient properly. Well, the trouble with acoustic applications is that we don't always know the sound speed in the patient. But what we do know is that they deform ultrasound images. So, yesterday, let me take a step back. Yesterday, Liliana Borsia presented a very nice method of inverting without knowing your operator, without knowing the wave speed exactly. Here, my approach is much simpler. I'm just simply saying that if we can get a decent ultrasound image, if we can get a diagnostic quality ultrasound image, it is subject to deformation due to sound speed inhomogeneity. That's the way ultrasound works. But the errors in my thermoacoustic range estimates will be comparable. And so we'll have very good co-registration to the ultrasound image that we've collected. So here's just a experiment that I did in my lab that was then corroborated during the argon experiment. If I use a single element transducer with a metal housing to transmit a signal to an ultrasound array up above, I measure a waveform that arrives after about 55, 60 microseconds. And if I back project that time series, these time series, I get this image here. And if I overlay it onto the ultrasound image that's created of that empty water field, I see my transmitting transducer, and the overlay in these two boxes is really very good. If I then, without touching either the ultrasound array or the transmitting single element transducer, I put stuff in between them. I change the sound speeds with a very high sound speed bone sample and a piece of gelatin, which is tissue mimicking gelatin, that's slightly different sound speeds. Well, what happens is I can still see barely that transmitting transducer in the ultrasound image. And the time series I get now, though, has been much refracted and bent around. And it's also shifted. It arrives sooner because we've got these higher sound speed objects in between. When I perform the same overlay, the agreement is very good. When I compare the two ultrasound images, I can see that the ultrasound transducer appeared to have moved by 4 millimeters. Well, in fact, it didn't move. It's just that the sound speed of the intervening material changed. That's exactly what happens in ultrasound imaging. So we're going to have to use the ultrasound images to deform back to the planning CT, which gives you very good absolute coordinates to get an absolute location of the Bragg peak. Okay, so in conclusion, we can detect thermoacoustic emissions generated during delivery of a clinical plan to an anthropomorphic imaging phantom. And I will say that the Gruneisens in the phantom are a little bit different than what we expect in soft human tissue, but not much. So I'm confident that we can do well in patients as well. In this phantom that wasn't moving, that's probably the biggest difference, we got very good results within a pixel of the planning CT. And one of the things that is really a big push these days is to hypofractionate treatments, to put patients on the table less frequently and deliver higher dose each time. So, many protocols now require patients to be treated over the course of many weeks, several dozen times. And part of the reason they do that is simply because they know that positioning errors will cancel out if you put the patient on the table 30 times. So a protocol that only requires positioning the patient 5 times really means that you've got to be absolutely certain you've treated correctly. So one thought is to bring the patient in, deliver a little bit of dose, check, and then deliver the rest. Additionally, there are new flash protocols that increase the deposition rate. And there's a clinical motivation for flash, which is the hope that if you deliver very, very quickly, the collateral damage is minimized. The healthy tissue is not damaged as much. That remains to be seen as an area of research, but certainly those protocols will increase our signal amplitudes. Another point is that thermoacoustic imaging is passive, so getting studies going is actually relatively easy. We can do a non-interventional study and just listen for sounds without changing the patient care. And then the final point I'll make is that these results are really very accurate relative to the ultrasound images that we can acquire. Now, the ultimate goal and my pandemic project has been to take this very cumbersome system and make it more user-friendly. And this work has been supported by a SBIR award through NIH. Okay, now my next steps, the first one right after this meeting is to work over my Austrian hosts for introductions to folks at MedAustron if possible, and then to complete validation of the 4-channel prototype, which was halted by COVID, and validate some new components that we've got and our more compact system. Okay, so with that, I can take questions. I hope I'm a little bit early.